Welcome to the talk on the paper-convex polynomial force motion model for planar sliding. Here, we'll see how the authors have proposed a planar friction model that connects an applied robot action to the resultant object motion. Think about what goes in our minds when we are trying to slide an object. Not much, because we have learned how much force we should apply to give it the right velocity via experience. But how would a robot determine these values? The difficulty lies in the fact that the contact between the object and supporting surface is an area-to-area contact with unknown pressure distribution. We don't know which part of the area is supporting how much weight, nor do we know the coefficient of friction. This makes object motion hard to predict. We want to find a connection between action applied by the robot and the object motion through something called a planar friction model. Hopefully, using a robot poke and some physics principles, we want to collect enough data about the object to be able to build this connection. But wait, what would sliding objects achieve? Well, there are numerous applications. The problem of planar robot pushing is an important feature in an industrial robot system which requires motions of pushing, controlled slip, and assembly of tight-fitting part activities. Also, understanding the mechanics of manipulation is essential for robots to autonomously interact with the physical world. The planar friction law relates planar twist and wrench. We'll constrain ourselves in two-dimensional velocity and force and explore the classical point friction law. In this model, the force of friction is in the same direction as the object's velocity if it is sliding. Otherwise, it could be any direction for a static object. Also, friction loads are within a circle and velocities are normal to friction loads. Assuming the principle of maximum dissipation, which argues that nature tries to maximize power for a given velocity and multiple choices of friction, we could have a generalized Coulomb's friction law, which only requires the friction loads to be within a convex set. The object used by the authors has 3 screws which are used as approximations of points of contact. Using the center of rotation at the red cross, we can compute the linear velocity at each point. Using the shown formulas, we can also compute force components and torque. The goal of the authors is to come up with a precise and data-efficient planar friction model under quasi-static assumptions, and such a model should be computationally efficient. The authors propose a level set representation of friction which can be computationally efficient without knowing the pressure. Given a convex function h of f that maps the input wrench to a real number, they use the one-level set to map the limit surface and gradients for velocity twists. The formulated function h of f, where the first sub-level set, or h of f is less than or equal to 1, represents the convex set of all generalized friction forces. The first level set, or h of f equals 1, corresponds to the general friction forces during slip, whereas the gradient of h of f represents the generalized velocity directions of the slipping case. Convexity, symmetry, shape invariance, and efficient invertibility are the 4 major properties required for this model to function properly. The authors show that strongly convex, even-degree homogeneous polynomials satisfy all 4 properties. The gradient of h of f represents the directions of the instantaneous generalized velocity during slip. They subsequently showed that strongly convex even-degree homogeneous polynomials are solutions which satisfy constraints such as maximum work inequality, symmetry, and scale invariance. The authors devised an optimization scheme to identify the coefficients of h of f from a set of f, v observed pairs. They enforce closeness of measured f's to the one-level set surface and align the gradient with measured velocities in the objective function itself. The constraints are meant to enforce convexity of the function. For evaluation, the authors compared the 4 candidate polynomial families as shown here, namely degree 4 convex and homogeneous, degree 4 homogeneous, convex quadratic, and Gaussian process. In the first simulation, a legged support with 3 points randomly sampled on a unit circle and randomly assigned pressure and uniform support with points uniformly distributed on the unit circle and squares with the same pressure were used. They also added some noise to the data. In real experiments, 3 screws screwed at different sets of locations underneath a triangular aluminum object were used. For the stable push action generation experiment, the authors report that degree 4 convex homogeneous polynomials achieve the highest accuracy and positive recall for different numbers of training examples. The metrics improve as the training examples increase. These findings will improve planar sliding, stable pushing, controlled slipping with dexterous hands, and assembly of tight-fitting parts. Thanks for watching! For more talks, visit scholar.stanford.edu.